Hello and welcome to my workshop. Now this is a lightweight fuel efficient sports car that weighs 415 kilograms, revs to 9,000 RPM and is incredible fun to drive. As well as being lightweight and fuel efficient, there are many other things that separate this from a modern sports car. It's designed to last for more than 10 years. It's designed to be easy to repair. It uses cheap, readily available parts. It uses a fraction of the energy and resources in its construction. And it also supports small businesses in your own area. In this video, I'll give a basic introduction to the design of the car, the aerodynamics, the parts used, and the different drivetrain options available. Following on from this video, I'll be releasing a multi-part video series that covers every stage of the build. I also have a book or ebook available that has instructions for every stage and includes all measurements and plans for the chassis, as well as a list of almost every part used and its weight. As you can see, everything is tightly packaged within the bodywork, so I've designed it to be easy and quick to remove. I've used Zeus fasteners, and there's one on top for the nose cone and 3 underneath. And at the rear there is one on top and one below, and there is also the wiring to disconnect. The main body shell has 6 fasteners underneath, as well as a fuel filler clamp to undo. The whole lot lifts off and can be laid down or stored upright. The cycle wings, or spats, have 3 fasteners each. Plus a wiring connector for each one. The wiring and brake lines run through the wishbone covers. It only takes a minute or so and everything is accessible. If we go back a few steps now, we can see the basic components of the car. There's a space frame chassis made mainly from 1-inch square tubing. And it has double wishbone suspension on the front and uses Ford Hudson brakes. It uses the same wishbones and components as the popular low-cost sports car, and all of these components are available off the shelf from various suppliers. And in the middle there's a motorcycle engine and gearbox. In this case I've used a 2017 Honda CBR 500R engine. This particular engine is an inline 2-cylinder, has about 50 brake horsepower, 40 Newton meters of torque, revs to 9,000 RPM, and has a 6-speed sequential gearbox. Obviously there are many other engines that can be used to suit your own taste, and I'll go over a few of those options later. And at the rear there is a Ford Sierra differential and Formula Ford double wishbone suspension. Something like a Hewland transaxle with its lightweight suspension and hubs would make a great choice for a car engine installation, but unfortunately not for a motorcycle engine. So I've designed this simple space frame subframe that not only accepts Formula Ford suspension arms, but also a Ford Sierra or Subaru differential. And I'm also working on my own rear suspension arm design that can accept a popular readily available upright that uses Ford parts. It will also have a slightly narrower track and use heavy-duty rose joints. In the future I'm hoping to add a supplement to the build manual for the rear wishbones with their measurements, as well as a supplement for the EV drivetrain that I'm currently working on. There are 3 main reasons as to why this car looks like this. Firstly, I wanted the bodywork to be as basic and simple to manufacture as possible. There are no compound curves, only single curves. The shape of the wings and the body can easily be achieved by wrapping or bending a sheet material to shape, be it aluminium, steel, plastic, or maybe even some sort of recycled eco-material. The top surfaces are just flat, so again it's a very simple to achieve shape. Secondly, I'm interested in car design and wanted to see if a car with only a 2-dimensional shape could still look and be aerodynamic. I also wanted this first car, or concept car, to be a blank canvas as it were, to be able to visualise future evolutions. So if you were to imagine the wheel cover as a foam block, you could trim and sculpt it down to your own more aerodynamic design. Thirdly, aesthetically, I thought it might look like a cool sort of 1990s sci-fi movie car, which I think it does. I also decided to use 2 small holes for the radiator inlets to act as nostrils for the headlamp's eyes and add a face or a little bit of character. Let's take a look at the aerodynamics now. I've tried to make the cross-section of the bodywork as near to a teardrop shape as possible, with a rounded front and a narrow rear to try and minimise the wake. For reference material, I've used George Cayley, whose works date to around the year 1800, and he pioneered the study of airfoils and low-drag shapes. I've also referred to the great German aerodynamicist Dr. Horner, who further refined the study of streamlined shapes. I've tried to follow some basic rules when creating the profiles for the wheel covers and bodywork. The length to width ratio of the profile or strut should ideally be 3.7 to 1. The widest point of the strut should be at around 1/3 of the total length. These figures are for two-dimensional profiles, so if the cover has a rounded top edge, the proportions change to 2.7 to 1 for the optimal length to width ratio. With regards to the cooling system, I've tried to make these two inlets as small as possible. Typically, radiator inlets are sized at around 40% of the area of the radiator. However, with an efficient design, this can be lowered to 20% or so. I've used the original motorcycle radiator, which is pretty small, so I've managed to get each inlet diameter down to about 70mm. In order for these small inlets to work, I really need a high pressure differential between the inlet and outlet locations. I've got a really good unobstructed feed to the front that forces air straight in. For the outlets, the best position would typically be just past the widest point of the bodywork. This would put the outlets quite far back and make the ducting tricky. However, when two struts are placed close to one another, the two sides work as a venturi, increasing the exit speed of the air and lowering the pressure. This means that I could place the outlets further forward and still maintain a large pressure differential. The only problem I have had with the cooling system is on a track day when the coolant would overheat when parked up immediately after a session. So I've fitted an electric water pump that will circulate the water for a minute or two after stopping the engine. I've also fitted an extra reservoir tank to the cooling system. I've also fitted some reprofiled coolant tubes to carry the coolant from radiator to engine. These have been flattened to increase surface area, and I've used thermal transfer pads to try and benefit from a little surface cooling. I've also fitted an oil cooler to reduce engine heat. Here the pressure differential is not so high, so I've used relatively larger openings. For more heat management, I've added ducts into and out of the engine bay to keep the temperatures down. There's an inlet and outlet on the side, and on the underside I've added 3 inlets. I've tried to keep the underside as smooth and flat as possible. At the rear, the exhaust has been positioned to fill in the wake and reduce drag. And under the exhaust is an electric fan and shroud that sucks some of the hot air out of the engine bay and straight into the wake area, which should reduce heat build-up and reduce drag. This is only a relatively small fan, but it would be fairly easy to drive a much more powerful fan mechanically via the drive shafts, which could not only cool the engine and reduce drag, but also create some useful downforce. On this car, I've tried to concentrate on keeping the airflow as smooth as possible and not on downforce. I've tried to keep all the protrusions as small and as clean as I can, and I've added small guides here and there to cover obstructions. There is, however, big potential for downforce as well as more drag reduction. For example, air curtains could be used. In this case, a curved one along the top edge would guide the air back on course along the car and reduce drag. These wheel covers should really have some sort of ducting to release air pressure inside the cover. On rounded covers, some vents on the top like this would be perfect, but in my case I have very poor flow along the top surface, so I'll likely add a long slit type vent on the inside edges and possibly a brake cooling duct. I used fairly sharp edges on the wheel covers and bodywork to accentuate its two-dimensional shape, but these edges should really be much more rounded to allow the air to flow easier over the edges. Likewise, along the driver's area, this should be much more rounded to reduce interference drag. And of course there's always the possibility of a fully enclosed cockpit. For downforce, there is plenty of space along the front and sides for dive planes and winglets, or maybe even a full front wing. There's excellent potential for movable aerodynamic devices, perhaps in the form of a wing that could rotate at a pivot and double up as an air brake. The most beneficial usage of downforce here, though, would be on the wheel covers or suspension arms themselves. The profile of these suspension arm covers that are fused are for low drag and have a very low angle of attack. More aggressive profiles with a higher angle of attack could easily be made up. The real benefit of this is that the downforce would be fed directly to the wheel. In most cases, downforce is applied down on the car's body or chassis, which compresses the suspension springs and thus reduces suspension control at speed. If the downforce is applied directly to the wheels, though, the suspension still has full movement at speed. The wheel covers themselves are also ripe for some extra downforce, possibly dive planes, or maybe their own little rear wings. On the underside, there's potential for diffusers or skirts. Here are some of the parts used. The wheels are from a Ford Ka. These were the narrowest wheels and tyres readily available with a Ford hub pattern. Front hubs are the old Ford Cortina Mark III uprights. However, there are lightweight alternatives available from kit car and motorsport suppliers. The sealed radiator unit uses the original motorcycle radiator and is made from readily available oil cooler ducts and knacker ducts. The steering column is a modified Mazda MX-5 column. Most of the motorcycle loom has been retained for the engine, immobiliser and dashboard. The dashboard is also from the donor motorcycle. The gear lever is forward for down and back for up and is connected by a control cable to the motorcycle's gear selector. The engine retains the original catalytic converter and so can get through the emissions regulations for road usage. Drive is taken from the engine to the diff by a very short drive shaft. This operates at quite an angle, so a slide-in shaft is used. A reverse gear is required now for road legality, so rather than use an expensive and noisy reverse box, I fitted a toothed wheel to the differential, which is operated by a starter motor. As mentioned, I do include a list of almost all the parts used, their weight and other details in my book or e-book. The engine is standard, although I did shorten the sump to lower the total engine height and added some extra capacity as well as some oil surge flaps. As you can see from this track day video, the oil pressure remains constant under hard cornering and braking. The suspension also coped well with high-speed corners and bumps under full load. The car is easy to drive and feels perfectly comfortable on the track with other cars. With regards engine choice, there are plenty of possibilities. The engine bay is around 700mm long and 500mm wide, although this could easily be modified to make it longer or wider. Single and twin cylinder engines are a good choice as they will easily fit into the narrow frame, which is essential for an aerodynamic design with a small wake. Something like this BMW flat twin engine would be an excellent choice, as it uses a drive shaft as standard and has a really low centre of gravity. Plus it would look great with its cylinder heads sticking out of the side of the bodywork. Electric motors could easily hook up to the rear diff, so would also make an excellent choice. Here you can see my EV version that has a Hyper 9 motor and uses Jaguar E-Pace batteries. The motor is around 90 brake horsepower and 200 Newton meters of torque. It should give a range of over 200 miles and also be far more efficient than a Tesla in terms of kilowatt hours per mile. Total weight should be around 450 kilograms without the battery pack, which will be about an extra 120 kilograms. Here I have a Renault Twizy motor with its controller and battery pack, plus an Alpha 33 transaxle. These could make an interesting combo and fit with a little redesign to the top of the rear subframe. There are also quite a few small 3-cylinder car engines or microcar engines that could fit directly to this Alpha 33 transaxle, or maybe even to a Hewland transaxle. With a suitable low revving car engine, 100 plus miles per gallon should easily be attainable, especially for those who enjoy driving on part throttle. For reference, this Honda CBR 500 engine with the Ford differential has a top speed of 72 miles per hour. I kept the top speed low as I wanted this to be a sort of sprint version that is as fun as possible to drive at legal speeds and to be able to achieve 50 miles per gallon under hard driving. However, this low gearing is at the expense of a comfortable cruising speed. By using larger diameter wheels, a lower ratio differential, or a modified gearbox, the top speed and cruising speed could be increased. As I mentioned earlier, there are many materials that could be used for the bodywork, and I chose to use fiberglass. For the wheel covers, I made a mould which is quite time consuming, but makes it much quicker and easier to replicate the wheel covers. For the main body shell, I needed a stiff structure that could lift on or off the chassis without flexing. So for this I used a sandwich construction with a 3mm flexible ply core and fiberglass skin either side. Here you can see 2 layers of 100-gram fiberglass are very weak, as is the flexible ply. But when you combine the two, you have an exceptionally strong but light material. First I made a buck to shape the plywood core. Then added fiberglass to the outside. And then the inside. This method with a more suitable core material could be used to make a combined chassis and bodywork monocoque structure that could negate the need for a steel chassis and massively save weight. I also used various other fiberglass techniques for other parts, like the oil cooler ducts or suspension arm covers. All of these techniques are covered in my video build series, as well as my ebook, which is currently available for a special introductory price of only £10, or about 1,200 rupees, or 100 won. There's a link in the description to my website. Another of the reasons that I built this car is that I'm a big fan of cycle cars and vintage specials. These are great little cars that come in a wide and imaginative range of layouts and styles, and is one of the most affordable ways into motorsport or car building. However, old car parts are becoming increasingly expensive and difficult to find, and their old-fashioned looks may be less relevant to future generations. So I'm going to suggest a new form of racing, hypermile racing, which would be a sort of modern version of cycle car racing. And there would be just two simple rules. 1. A weight of under 450 kilograms. 2. At least 75% of the wheels must be covered. Races would be run with a set fuel limit. So as an example, a 20-lap race of a 2-mile circuit like Brands Hatch would be 40 miles, for which 1 gallon would be allowed. For electric cars, the equivalent of about 10 kilowatt hours would be allowed. This effectively means that the car that can drive fastest at 40 miles per gallon would win. Another good example of a potential fuel race could be a 1-litre Nürburgring challenge. Who could drive the fastest lap of the Nürburgring on 1 litre of fuel, or about 2 kilowatt hours of electricity? Again, this would equate to around 40 miles per gallon, and would be a far more challenging and technically inspiring feat than the traditional fastest lap of the Nürburgring. There could also be a power limit of say 100 horsepower or maybe a maximum tyre width, although a set fuel limit would probably negate the need for extra rules like this. I've used the 450 kilogram or 990 pound figure, as this copies the quadricycle system that limits the weight to 450 kilograms without fuel. This means that electric versions can be built to 450 kilograms excluding the battery pack, so this should make it easier for electric cars to meet the weight limit. It means a Renault Twizy like this, or this, would only need a set of wheel covers to race. It would also be open to vintage specials and cycle cars that would likely only need a nice set of aluminium wheel covers to race. A really useful source could be unfinished Lotus 7 style projects that regularly turn up for £1,000 to £2,000 on the internet. And with the addition of some aero bodywork and a lightweight engine would also be illegible. Inspiration for other covered wheel designs could come from low drag designs of the past. Something like this, or this, or maybe the index of efficiency race cars that used to race at Le Mans. So this would be a race series that, like cycle cars and vintage specials, is affordable, sustainable and creative, but would offer extra variety and modernity. It would allow for racing between vintage and modern cars, as well as racing between petrol and electric. It would promote all the traditional skills of cycle car building, such as chassis construction, suspension design, metalworking and engine building, but also add new skills such as computer-aided design, 3D printing, composites, aerodynamics and downforce. I'm just putting out this idea, should there be any other like-minded people out there. If we could gather 5 or 6 cars together, we could start a little race series. Now finally, I'm going to talk about what skills are required to build a car like this or something similar. Firstly, you don't need a fully stocked workshop. For tools, a few hand tools, some basic power tools and a welder should do. This workshop is actually only served by a double plug socket, and that's all you need. And you don't need to be a professional mechanic either. All the skills that I needed to build this car were learnt from friends or from watching YouTube videos. There's no particular or specific skill that you need to excel at to complete a scratch-built car or project. And out of all the skills required, I would say that imagination and self-belief are far and away the most important. And you may also be worrying or thinking that it's a lot of effort to build your own car, and it is. But you only have to look at the cars being built today to see that the car manufacturers have no interest at all in building lightweight or sustainable cars for you. If you want something lightweight or different, you're going to have to build it yourself. You are not on your own, however, because you have a community of like-minded people all around the world who are willing to share advice and information for free via the internet. And you also have a community of like-minded people local to you who can help. For example, maybe you're into electrics and you could easily modify a used EV battery pack and motor yourself. You might then find a local welder and suggest that if you were to build a couple of motors and battery packs yourself, and he or she a couple of chassis, then you could swap one for the other. You could then help each other to finish off the parts of the build and end up with one each. Maybe you don't have any specific skills, so you can go to your local car club and talk to other members. Perhaps someone has experience in fiberglassing, another can weld, and another has access to spare garage or workshop space. So you get a plan together and start building. Once you've finished that car or cars, you find that you have real-world experience in manufacturing, chassis construction, project management, budgeting, quality control, as well as having a good set of contacts. You now have everything that you need to start your own business. And this idea can be scaled up. Instead of waiting for our manufacturing industries to disappear altogether, we can use what useful features are left to build our own manufacturing infrastructure ourselves. With the help of like-minded communities around the world, we could have a series of small, sustainable businesses run by working people and manufacturing all sorts of complex goods for the benefit of local people in their community and keeping the profits within that community. And it doesn't work just for manufacturing, it also works for food, energy or housing. And can you imagine that? A series of small, sustainable businesses providing decent and affordable manufacturing, energy and food for you and your community. And it all starts by building something.